I guess we can start. So remember what we were doing last time. We were talking about invertible phases, and we started with an example of an invertible phase of fermions with no symmetry other than fermion parity in 1 + 1 dimension. And we had this very explicit Hamiltonian. So we have a Hilbert space with a fermion sitting on each side, and then we write it in terms of these Majorana fermions. And we couple them in this manner. And we saw that when the chain is closed, then there is a unique gapped ground state. When the chain is open, there is a protected twofold degeneracy associated with the two boundaries. Okay, so this is an example of a non-trivial invertible phase. And remember, we said that invertible phases form an abelian group under stacking. So let's, using this particular phase as a generator, let's try to understand what happens under stacking. Right, so let's take two copies of this chain, and let's stack them together. So first, let's ask whether we can gap out. Let's consider an open chain, and let's ask whether we can gap out the boundary Majorana modes. So I don't know, let's call this eta1 here and eta n bar here. So each chain contributes a dangling Majorana mode, and let's see if by adding perturbations, coupling the two chains, we can gap out the boundary modes, and the answer is obviously yes, right? So if we consider delta H equal to I gamma 1 eta 1 plus I gamma n bar eta n bar, these are local terms localized on the boundary that will gap out the boundary Majorana modes and lead to a fully gapped ground state on an open stacked chain. So generally, this is a kind of a good diagnostic. If you can gap out the boundary, then the invertible phase is trivial. So this is this suggests that two copies of Kitaev is trivial. So 1 + 1 is equal to 0, where I'm thinking of a single Kitaev chain as a generator under stacking. Yeah. Now, in this particular case, we can actually do better. We can begin with, in addition to this boundary argument, we can really show that two copies of a Kitaev chain are continuously connected to a trivial product state. So let's again try to draw this. Maybe I should have prepared infinitely many copies of this quantum state. Right, so let's think about two closed chains and stack them. And this is the Kitaev Hamiltonian drawn pictorially. And remember how the trivial chain looks, right? Where you only have coupling on each side. So trying to keep the same x coordinate. But okay, so this is gamma 1 bar, gamma 2 bar. And so forth. Gamma n bar. Right, so we want to find a path in Hamiltonian space that connects this Hamiltonian to this Hamiltonian. So kind of repairs the Majoranas. And in the present case, that's pretty easy to do. So first, the idea is that first we kind of divide the system up into these blocks here. And in each block, you can find a path in the Hamiltonian space that will move the bonds from horizontal to vertical like this. Right? So really, if you think about 4 of these Majoranas here, right? So that's 2 complex fermions. So that's a 4-dimensional Hilbert space. And in a finite dimensional Hilbert space, if I have 2 Hamiltonians and 2 ground states of those, 2 gap ground states of those Hamiltonians, I can always connect those 2 ground states, preserving the gap, as long as the 2 states have the same quantum number under whatever symmetry I have. In this case, the only symmetry is the fermion parity. So all that I need to show is that this state and this state have the same fermion parity. Okay, if you if you do it right, there is some sign involved in choice of the coupling here. But if you choose the sign in the same way, then the fermion parity will just be even for both of these, both for the horizontal bond configuration and for the vertical bond configuration. So then you connect to bonds being horizontal, and you do this independently for each block. And now, once the bonds are horizontal, right, now you can play this game again and rotate them to be horizontal like this. Which is exactly the picture at the bottom. Right? So this is an explicit path in the Hamiltonian space connecting 2 copies of the Kitaev chain to a trivial product state. So that shows that the Kitaev chain indeed generates a Z2 group under stacking. And in fact, turns out that the Kitaev chain is the only non-trivial invertible phase of fermions in 1+1 dimensions if there is no symmetry other than fermion parity. So you can actually prove that using more sophisticated methods. So very good. So this is the stacking structure. Yes?
Could you please clarify the first example? Because I think last time we discussed that when we have degeneracy of ground state, we cannot go to trivial phase because once we leave this degeneracy, the gap should be closed. Yeah. But now somehow it worked out.
So, this issue of connecting 2 states in the Hamiltonian space, right? We are always, in that case, working on a closed manifold, right? So here I was saying that a diagnostic of whether an invertible phase is trivial or not is to see whether you can gap out the edge preserving all symmetries. So that's kind of a different way of diagnosing whether something is trivial or not.
So we don't want to do the continuous transformation here. We are fine with just adding delta H with
right. So here the name of the game is we start with some bulk state. Initially maybe the boundary is gapless, like before we turn on these couplings here, and then we want to find some Hamiltonian, some perturbation of the Hamiltonian on the boundary that will gap out the boundary modes. Yeah. Okay. Okay, so far, when we talked about the Kitaev chain, the only signature of its non-triviality that we saw had to do with the boundary modes. Can we somehow diagnose the non-triviality of the Kitaev chain without cutting it up, without exposing the boundary? And there is actually such a diagnostic, which is threading flux or changing boundary conditions on a circle. So, and this diagnostic actually turns out to be kind of very general tool for diagnosing whether something is a non-trivial invertible phase. So let's talk about bulk signature of Kitaev. So what we are going to do is, now I'm going to draw my, begin by drawing just the fermionics, just the original sides of the model with the fermions living on them. And then here is Cn. And what we are going to do is we are going to couple the system to a background connection for the only symmetry that we have in the game, which is fermion parity. Okay, the words that I said are, strictly speaking, not correct. We are going to twist the boundary conditions for the fermions, and right. So we are going to insert a twist defect somewhere along the closed chain. So now I'm thinking about a closed periodic boundary condition to start with, and then we want to insert a twist defect here. So this is a general thing that you can do. If you start with a Hamiltonian, if you think about a cut somewhere, then you can write the Hamiltonian of the system in the following way. Terms which only involve the sides on the left, terms that only involve the sides on the right, and then the terms that couple the left and right sides, O left alpha, O right alpha. So there is some number of terms like that where O left and O right are both localized. O left only acts on the left side and O right only acts on the right side. Okay, and if we have a symmetry U of the form that we discussed last time, so an on-site symmetry, then we can consider a twisted Hamiltonian, twisted by this group element G, and so let me call this H left right, and the twist amounts to rotating all the operators, say, right of the cut in this sum by the symmetry U. Like this. And because U is assumed to be an on-site symmetry, this conjugated operator also lives just on the right side of the, acts only on the right side of the system. So it's of the same form that we started with. Moreover, well, you can move the location. Right. So you can move the location of this cut using the fact that the Hamiltonian that we started with is symmetric. So it's kind of like a gauge. You can perform a gauge transformation that moves the cut around. Right? So this is definition of a twist defect on a lattice. So we can study now the response of the system to such a twist defect. That is, we can study the eigenstates of the twisted Hamiltonian, in particular the ground state. So let's apply this to the Kitaev chain. Let's draw another. Maybe I'll just recycle this.
Yeah. So is this the same as applying, like, if I take UG and I apply it to like half the system?
You have to be a little careful, right? Because I'm thinking, say, here about periodic boundary conditions, right? So if you apply it to half the system, then you create two twist defects. Whereas here I created just one twist defect. So two twist defects kind of in a circle topologically is trivial, but one twist defect is non-trivial.
So in fact, from h equals h left plus h right, this was a bit confusing. In fact, h left plus h right is everything except for that link. There's no left and right. Everything else is continuously connected to each other.
That's correct. So I only, well, there is a cut, right? There is a cut, and everything away from the cut, and then only the terms that connect the two sides of the cut get conjugated. It actually, well, this was the comment I made, which is that the naive translation is broken by the choice of where you put this cut, but there is a combination of translation and a gauge transformation which is preserved. So effectively, this doesn't break the translation symmetry. So in the path integral formulation, in the space-time path integral, this corresponds to a topological defect line, just going up in the vertical time direction. Okay, let's draw this Majoranas again. Like this. Okay. So let's remember this is site 1 here, gamma 1 bar, gamma 2 bar. Let's thread this flux. Let's put a twist defect between sites n and site 1. Okay? Twist defect of what, right? It has to do with the twist defect of a symmetry. Well, in this Kitaev chain, the only symmetry we have in the game is the fermion parity. So we're going to put a twist defect of the fermion parity at this location. Now, remember, well, how the Hamiltonian looked, right? This Hamiltonian was sum j equal 1 to n I gamma j bar gamma j plus 1. So this cut, it only separates, the only terms that are affected by the twisting will be the ones connecting gamma n bar to gamma 1. Right, so here, what I called h left right there is I gamma n bar gamma 1, and I'm supposed to perform the twist. I'm supposed to conjugate gamma 1 here by -1 to the fermion parity. So it's going to pick up a minus sign. Just write like this. Bar gamma 1. Okay. So if previously, before we put in the twist, the ground state carried I gamma n bar gamma 1 times ground state is minus ground state. This now goes after the twist plus the new ground state. Let me call it twisted ground state. Okay, so
we change the Hamiltonian and we have a new ground state.
That's right. Yes. And what we'll see is that this change corresponds to the fermion parity of the ground state switching. Remember when we were talking about an open chain with two boundaries, we saw that effectively the fermion parity of the ground state became something like I gamma 1 gamma n bar. And now we are switching, now we are connecting up these two Majoranas, and we are switching the sign of I gamma n bar gamma 1 in the ground state, so the fermion parity of the ground state switches. Let me write that down. Remember, -1 to the f, when we considered an open chain, effectively became I gamma n bar right, I gamma n bar gamma 1. So -1 to the fermion parity on the ground state of the untwisted Hamiltonian gives me -1, and -1 to the f on the ground state of the twisted Hamiltonian gives me +1. So the fermion parity switches. Right? So this is a nice diagnostic of the Kitaev chain, which doesn't involve actually opening up the boundary, just involves threading, if you wish, a pi flux through this closed ring. Now we can.
Do you imply that if you were to do the same trick for the trivial,
nothing would happen, right? Because for the trivial chain, the Hamiltonian is just Ci dagger Ci. So in fact, there are no terms, and the ground state is characterized by Ci dagger Ci equals 0. If I try to thread a flux here, right, there are actually no terms that connect the two sides, so it just doesn't do anything. And that's always the case. A product state just doesn't respond in any way to flux.
Would this kind of argument work for the bosonic invertible phases?
Yeah. Yeah.
Which symmetry would you twist?
So in 1+1 dimension, for the bosonic,
yeah, like the table that we saw yesterday, like there were some non-trivial.
Well, so it's for bosonic phases enriched by symmetry in 1+1 dimension, because in 1+1 dimension there are no bosonic phases without symmetry. Yeah.
In 2+1.
Yes. So arguments like this in general are quite useful. In 2+1, what you want to do, well, okay, the question is whether this is exhaustive or not. And turns out that if you do it right, it's exhaustive. Or ideas like this about inserting fluxes turn out to be exhaustive. Okay, let's think of the same thought experiment, but expressed in terms of the partition function of the theory on two torus, right? So let's see, what can I? Two torus. So here is the spatial direction. This is the time direction. And, well, if I don't put any fluxes, then the usual partition function, right, of the system is just trace of E to minus beta h, where h is the Hamiltonian, in this case acting on a closed chain. And I'm interested in the limit when beta is large compared to the inverse gap of the system. So then it's only the ground state that contributes to this trace. When beta delta is much bigger than 1. So the ground state energy is some non-universal quantity, which I can always tune to 0 by properly adjusting my Hamiltonian. So then I'll just tune it so that this partition function becomes 1. Right? So then if I just calculate this partition function, either for untwisted boundary condition or for twisted boundary condition, there is a unique ground state, so this partition function will be equal to 1. I can also consider, instead of usual partition function, I can insert -1 to the fermion parity into this trace.
Can I ask a question? So are you assuming that so you tuned in the phi equals 0 sector, you tuned the ground state energy to 0.
Yes.
Then you tread the flux. Okay, here we have a simple example where everything is free. I say that even in the presence of interactions, the ground state energy is not going to change.
That's
stay
right.
0.
That's right. Or exponentially small in the system size. Yeah. Because this flux, you can kind of move it around. It's kind of like a, okay,
Wait.
what's it? Sorry?
Plausible, yeah.
There's probably some argument one can make. Just, you can think about expectation value, and you can kind of each term in the Hamiltonian, and you can probably kind of move the cut out of the picture for each local term. So there's probably some argument that you can make as long as your state is gapped.
I have a question.
Yes?
How do I understand this twisting as the same as stacking and understand?
Oh, this is not stacking. This is a separate.
But aren't you using it to say what the group would be of the?
Not directly. So we concluded that the group is Z2, and now we are trying to find signatures of the one in this group, of the generator of this group, without opening up the system, just considering a system on the ring. Yeah. Okay, so I can also look at so here I kind of twisted when I looked at the partition function with flux pi, I twisted my boundary conditions along the spatial cycle. I can also twist them along the temporal cycle, and that amounts to putting in -1 to the f into this trace. And this just picks up the fermion parity of the ground state, right? If there is a, in this same limit beta to infinity. So this picks up the fermion parity of the ground state times the ground state energy. So when I didn't thread any flux in, the fermion parity was -1. When I threaded flux through, the fermion parity was +1. Okay, so let's write down all four. Let's make a little table. Maybe we'll make it here. So we have two directions on the space-time torus along which we can twist, and we can have antiperiodic or periodic boundary conditions for the fermions along either of the directions. So sometimes these are known as Neve-Schwarz and Ramon. Now, when we take the usual partition function without inserting -1 to the f, remember that actually corresponds to antiperiodic boundary conditions on the fermions in the time directions. That's when you go to the Grassmann path integral. So this corresponds to c of tau plus beta equal to minus c of tau. So when we put in the -1 to the f, that actually corresponds to the periodic boundary condition for the fermions along the time cycle. So, and then, you know, so this is, let's say this is x and this is tau twist. So for the spatial coordinate, we just untwisted is periodic, twisted is antiperiodic, and filling in this table, we get a pattern like this. So quite interesting. Okay. So we saw that for the Kitaev chain, the non-trivial 1 + 1D fermion invertible phase, we can detect its non-triviality just from the bulk partition function by considering the bulk partition function in the presence of different boundary conditions or threading in different fluxes of the fermion parity symmetry through the different cycles of the torus. And this will turn out to be a general strategy for detecting non-triviality of invertible phases. We'll need to place the theory on some closed space-time manifold, and the partition function on that closed space-time manifold, possibly in the presence of some background gauge fields for the symmetry group. If you have a symmetry group, will tell you about will characterize the phase. Yes?
So, is it a matter of convention which one is which one's +1 and which one's -1 for the twisted versus spatial twisted versus untwisted?
It is somewhat a matter of convention. In the field, in the field theory description, it's not a matter of convention, but what in the exact microscopic model, I believe whether the actual periodic boundary condition maps to the periodic boundary condition in the field theory or not, that I think is microscopic detail. But we can think about it.
I guess if I just change the sign of everything in the Hamiltonian.
Yeah, well, then there is also maybe some even odd. You can also get some even odd effect depending on the length of the chain.
There's also ambiguity in the definition from a pair. Usually we just choose the NSN sector to be more.
Well, that's right. So there, one question is microscopically, and the second question is in the field theory, and the question is whether kind of the obvious choice in the microscopic model corresponds to the usual to this assignment in the field theory, and I think the answer is no. There is some ambiguity, but left as a homework exercise.
One question. So you insert the defect of around temporal direction and around the spatial direction to detect the invertible phase. This is general and does not require any Lorentz symmetry.
Well, so here you see there is no Lorentz symmetry. So here, the nice thing about the Kitaev chain is that we could already detect its non-triviality by working on a space-time torus. For more general invertible phases, you actually cannot. The torus will not suffice. You will need to consider a more complicated space-time manifold. In which case, which is problematic if you have a lattice model. But so then you need to really have some kind of continuum quantum field theory.
So still the Lorentz symmetry is not important.
Not important. At least not here. Yes.
So even if you can't detect it on a torus with these flux kind of insertion arguments, it's still sufficient to diagnose.
So in general, if you consider the theory on the most general space-time manifold and thread the most general fluxes through the holes of this space-time manifold, you should be able to detect the phase. Yes, that's actually where we are going. So we are now going to learn how to place this Kitaev chain on an arbitrary space-time manifold. Yeah.
Would it be wrong to think of the taste defect as some kind of order parameter that lets you which way is
There is a perspective like that as well, where you can act with a symmetry on a finite region of your system, and then you kind of heal. You kind of heal the action by acting at the boundary of the region. So this is kind of like a string order parameter. And exactly the details of this string order parameter can be used to diagnose the phase as well. I was thinking of that as a homework problem, but I haven't written it up yet. Yeah, there are always different perspectives that one can take. Okay, so placing Kitaev on a manifold. Okay, so again, we are now going to try to place this theory not on the torus, not on the space-time torus, but on some general space-time manifold. And this is going to be a Riemannian manifold in 2 dimensions. So we're going to be in Euclidean or Riemannian signature. And obviously for this we need some kind of field theory description of the Kitaev chain. And how do we pass? I'll explain how we pass to a field theory description. Actually, it's quite natural in this case. So remember, we had these 2 Hamiltonians. One was a trivial, realize the trivial product state, the other realized our Kitaev chain. And now let's consider a family of Hamiltonians that interpolate between these two. Where lambda is a parameter running from 0 to 1. So clearly, the gap has to close along this path, right? Because we just learned that these two Hamiltonians are in different phases, so I cannot go between them without closing the gap. And actually, the gap closes at a point lambda equal to 1/2. Just midway, delta goes to 0. Let me draw the Hamiltonian for lambda equal to 1/2. Well, you kind of have equal coupling on side and between sides. So just draw it here. H of lambda equal 1/2 looks like this. It's just equal coupling. Okay. Etc. Gamma 1 bar, gamma 2 bar, gamma n bar. Okay, so let me write down the Hamiltonian actually. So this is still a free fermion Hamiltonian, so it can be diagonalized exactly. H lambda equal 1/2 equal to 1 to n I gamma j bar plus I gamma j bar gamma j plus 1. And when you diagonalize it, like that, what you find is that the single particle dispersion has the following shape. So this is 0, momentum 0, and energy 0. So what you find is that at low energy, you have one right-moving Majorana fermion and one left-moving Majorana fermion. So the theory becomes gapless. And the Hamiltonian, if I take the continuum limit, which means I focus on the region near momentum 0 here and energy 0, where these are the usual one-dimensional Majorana fields, chi left and chi right. So chi right of x, chi right of y is something like delta of x minus y. Okay. And when I tune lambda away from 1/2, that just corresponds to turning on a mass term for this, coupling the right and left moving Majoranas. I am dx chi right, chi left. So m for lambda close to 1/2 is proportional to lambda minus 1/2. So lambda equal 1/2 is the phase transition between the Kitaev phase and the trivial phase, and we see that the phase transition is described by this simple 1 plus 1D conformal field theory, free Majorana. So let's write it down. The m greater than 0, mass greater than 0 is then the trivial phase, and mass less than 0 is the Kitaev phase. Okay, so this is the bulk spectrum. Now you can show that if you create a spatial interface between this trivial phase and the Kitaev phase, then in addition to the right, so let's see. So let's say you have this is x, this is m less than 0 and m greater than 0 here. Then you'll find that while in the bulk everything is gapped, on the boundary you'll have Majorana modes in this theory. So I'm now thinking of making this m to m of x. You will have this Majorana modes, that is zero energy modes localized at the two ends, localized over length scale of something like 1 over m. So that's a good exercise for you to try out. Just coupled to some profile. I think you can probably even do it for any profile and show that there are zero modes localized at the two ends. So this corresponds to the Majorana zero modes at the end of the chain that we previously found, right? Well, previously we just had a finite chain. The outside of the chain was vacuum, but you can think of vacuum as the trivial phase. So that's correspondence with this continuum picture. Questions? Okay.
Is it obvious what order the phase transition is?
Well, in this case, it's second order, right? It's just described by the scale invariant theory. Yeah.
So in your spin chain description, when you classified phases, it was important for you to know that some gammas came from the same C and other gammas came from another C. And when you get past to the continuum limit, you lose this information. You just have Majorana fields, everything in the continuum. So how do you still, is there some convention which allows you to say what is trivial and what is trivial?
I think once you come to the continuum description, you don't know which one is the trivial and which one is Kitaev. So there is some convention. If you don't know where it came from, then there is some convention, and we'll discuss how to deal with that. So you can always add how are they called, counter terms, right? So and this freedom of adding counter terms is exactly the ambiguity that you're talking about.
If you keep this lambda, can you map it to the mass?
You can exactly. Here you can do everything exactly. You can find, well, okay, so first of all, this is the continuum limit, but you can exactly solve the, so this is the limit when lambda is close to a half, but you can solve this problem exactly for any value of lambda, right? Because just free fermion problem. So now, once we've gone to this field theory continuum description, now we can place it on any space-time manifold. Because this theory in the continuum has an emergent Lorentz symmetry. Right? So if you are working in flat Euclidean space, then let me make the Lorentz symmetry manifest by writing down the Lagrangian. Maybe I'll keep this Let me think. Just erase this. Write it like this. C dagger gamma mu d mu plus m chi. So I'm writing a Lagrangian instead of a Hamiltonian. Chi is just chi right, chi left. Mu runs over 0 and 1. C is the charge conjugation matrix. And with the notation I have there, basically, there is some choice of gamma matrices that makes this work. And these gamma matrices, as usual, satisfy the Clifford algebra. And then C gamma mu star C dagger is equal to minus gamma mu, and gamma mu are Hermitian, so this is in Euclidean space, flat Euclidean space. Okay, so theory has emergent Lorentz symmetry, and this allows us to actually place it on arbitrary space-time manifold, not just on the infinite Euclidean space. So this is the standard going to curved space. How to couple this Majorana fermion to a metric. So the action becomes something like this, where the Dirac operator D takes this form. So E is the Wilbachian, gamma A are the same matrices, gamma naught, gamma 1 here, omega mu is the spin connection, G is the metric of your space-time manifold. So I will not go into all the definitions of these quantities related to the geometry of the manifold. It will not be very important, but probably if you look at the text by Nakahara or someone like that, you can learn this stuff. And this is integral over the manifold. Okay, so this is the action. So we managed to place Kitaev on an arbitrary space-time manifold, just given by a massive Dirac. The transition point is the massless point, but the Kitaev phase is the case when this mass is finite, but of an inverted sign. Inverted relative to what? Well, relative to the trivial phase. And now we will study the partition function of this theory on an arbitrary space-time manifold.
Yeah. Is that possible to do a space-time lattice and use a Partition to get a discretized version of
discretize this?
Yeah.
I think so. Yeah, I don't see why not.
Like encounter fermion doublings and so on.
But here, right, so there is no anomaly, at least not of the usual kind in the bulk. So if you break, maybe you'll need to break some kind of reflection symmetry, but even that, right, so here,
fermion doublings appear without anomalies sometimes. Like this PCB people have to be very smart.
But here, the fact that on the flat space-time you were able to do it, right? There is no issue. There is one right moving Majorana, one left moving Majorana, which we got from this very concrete lattice model. So that means that you don't run into problem with fermion doubling.
can I ask a question? So this can be done on any orientable, non-orientable. There's no question here.
So here, at this point, we will work on oriented 2D manifold with spin structure. Right, to put a fermion on a manifold, we need a spin structure. You know, we have the spin connection here, so it's kind of part of the data. And we already saw that the spin structure is very important because the partition function does depend on the spin structure. Okay, so how do we calculate the partition function of this theory? Well, it's a quadratic theory. So the partition function can be calculated directly. It's going to be a fermion of this operator. Let's go here maybe. So the partition function Z going to be a function of the mass m on a manifold with spin structure is going to be d chi minus s of chi, which is symbolically or formally the fermion of this antisymmetric operator here. Right, so this is a Grassmann path integral, C dagger plus m. Remember, if you have a Grassmann path integral like this, then and A is an antisymmetric matrix, then this is the fermion of A. Okay, so now we have to calculate this fermion, but with fermions there is always issue of the sign, right? So we'll have to figure out what's the correct sign, whether there is some ambiguity of the sign. And we'll find that we can circumvent that problem by using the reference state, which is the trivial state. So, okay, let's get to work. So first, I'm going to express this fermion in terms of the eigenstates of the d slash operator. Let's see where. Oh, let's go here. So this operator minus I d slash is Hermitian. So it has real eigenvalues. And okay, we can normalize. Well, it's Hermitian with respect to this inner product on the manifold. Can normalize this in the following way. And moreover, actually, this operator, the eigenvectors come in pairs, where to each eigenvector phi lambda, there is a pair eigenvector c times phi lambda star, right? Where c is this charge conjugation operator and star is just the complex conjugate. So these have the same eigenvalue, but they are orthogonal. And now, expanding my Grassmann field chi in terms of this eigenvectors, eta lambda 1 phi lambda of x plus eta lambda 2 c phi lambda star of x, where the prime means that I, for each pair of eigenvalues, I keep only one term. After this, the action in terms of the Grassmann variables eta1 and eta2 takes the following decoupled form. Okay, it's antisymmetric as necessary for a Grassmann variables. So we managed to kind of block diagonalize this operator C dagger d slash plus m.
So is that the only degeneracy?
Well, there can be more, but this is the one that will be useful to us. Okay, so now it's easy to take the phi of this big matrix because it has become block diagonal. So Z m of m is just going to be product over the eigenvalues lambda of phi of each one of these 2 by 2 matrices, and that's just I lambda plus m. But why plus I lambda plus m and not minus I lambda plus m? That sign really depends kind of on the orientation on your Grassmann variables here. So how do we figure out the sign? Well, the trick is that we can look at the ratio of partition functions with different mass. And that ratio, the sign will cancel out in that ratio.
What is that prime in the
So we only, these eigenvalues come in pairs, or eigenvectors come in pairs, and we count each pair once in this product.
This transformation, it leaves the eigenvalue invariant, but changes only the eigenvector.
That's correct. And these are orthogonal because C is an antisymmetric matrix. So C star C is equal to minus 1. So this is like a Kramer's time reversal if you wish, but at least formally.
Is this actually the consequence of the symmetry?
So this is actually kind of because of the doubling, right? I don't know whether that. It doesn't correspond to any physical symmetry of the microscopic theory, but it just corresponds how to best. This is just kind of in this free fermion formalism. This is a useful symmetry. It's kind of maybe related to CPT. Well, but there is no charge, right? So in the free fermion description, this is what you would maybe call C, but there is no kind of many-body symmetry associated with this. This is kind of a dummy symmetry, if you wish.
So are all the lambdas non-zero?
No, they can be 0. Actually, yeah, they can be 0. We'll see in a second that the 0 eigenvalues actually play a very important role. Okay. Right. So what I propose to do is look at the following ratio. Oh, I should have erased this. Z of M over Z of some big mass M here. So this is the ratio of partition functions. And remember, you have this mass, so here's maybe trivial, there's 0, trivial, Kitaev. So let's say positive mass is the trivial. Then as we're tuning the mass across this transition, then on a finite manifold, the partition function should be smooth, right? The partition function can have some singularity in the thermodynamic limit, but on a finite manifold, it should be smooth. And that makes the sign unambiguous in this ratio. Okay. Furthermore, if positive mass is the trivial phase, then we expect that the partition function here should be the same as the partition function of a trivial Kitaev chain, just product of a product phase, product state, up to local counter terms. So we expect that Z of M is equal to 1 up to local counter terms. So I'm kind of start with infinite mass, and then as the mass is decreased, you might generate some local counter terms, say, maybe a cosmological constant log lambda over mass. Sorry, root G. Okay, this is actually not cosmological constant. This is something else, because this has the curvature. So this is something proportional to the Euler characteristic of the manifold. But only we expect that in this phase with positive mass, we only have these local counter terms that we can tune away. So then, effectively, I'm going to think of this ratio as the partition function of the, when m is negative, of the non-trivial Kitaev phase up to local counter terms. And in fact, it will be, in the present case, convenient to just look at the ratio of partition function with positive mass to that with negative mass. So we're just going to look at, we'll call Z Kitaev of manifold spin will be the ratio minus m to Z m, which will be a product like this. Okay. Now, there is one more thing about the spectrum of this operator that I need to tell you, which is that in addition, the eigenvalues come in pairs of positive and negative eigenvalues, because there is a matrix gamma 3, which in this case is sigma 3, which anti-commutes with d slash. So the eigenvalues actually come like this. So there is a pair of positive eigenvalues, say, and to each pair of positive eigenvalues, there corresponds a pair of negative eigenvalues. So then I can write this as product over just positive eigenvalues, I lambda minus m minus I lambda minus m over I lambda plus m minus I lambda plus m times the product over the 0 eigenvalue pairs. And when lambda is equal to 0, this is just minus 1. But this term is 1. So I just end up with minus 1 to the number of 0 modes of d slash divided by 2. Divided by 2 because of this prime. And so the 0 eigenvalues also come in pairs. Okay, so that's a very simple expression for the partition function of the Kitaev chain. Now on arbitrary manifold.
So this happens because you divide it by this ZN.
That's correct. So I'm saying that the partition function must be this up to local counter terms. And I've tuned away these non-topological local counter terms. So the partition function is equal to plus or minus 1. Very simple. Z Kitaev is equal to plus minus 1. Moreover, it's a topological invariant. Right? So suppose we change the metric on our manifold smoothly. Right? Then what happens to the spectrum? Well, you can have a pair of eigenvalues come down, but then by the symmetry of the spectrum, this pair must come up, and the number of 0 modes will change by 4 as this hit the energy 0. So the partition function doesn't change. So this is topological.
Is it obvious that the number of 0 modes is even?
By the same argument, right? Because for every eigenvalue, there is another one obtained by complex conjugating times c. Yeah.
Sorry, this is the ARF teacher.
This is exactly the ARF invariant. We'll talk about this. For those of you who know what an ARF invariant is. Okay, so let's do an example that we actually already saw. Let's take a torus manifold, which is a torus. Okay, so now we are supposed to look at the spectrum of this operator D on the torus, on the space-time torus. Well, the spectrum, the eigenvalues lambda, are going to be kx squared plus ky squared, where kx and ky are the x and y components of the momentum. And, well, right. So, okay, it's flat torus, right? So all of all of the spin connection, all of this business goes away. It's just a Dirac operator on flat torus. And clearly the only zero modes are when kx equals 0, ky equals 0. But to have this momentum allowed, you must have periodic boundary conditions on the torus. So when you have anti-periodic boundary condition along either of the two directions, there is no zero mode. So the only zero mode appears when you have periodic boundary conditions along both directions. So anti-periodic, periodic, anti-periodic, periodic. So here, everywhere, number of zero modes is 0. The partition function is 1. When kx and ky are equal to 0, well, you have this is a 2 by 2 matrix. D goes to 0, so you have two zero modes, 1, 0 and 0, 1. So in this case, for periodic, you have number of zero modes is equal to 2. So the partition function is equal to -1. So that's exactly the kind of result we obtained earlier from our lattice model.
And you see the degree. You need to take M go to infinity so that the first term that factor drop off.
In this particular example, you don't need to take M to infinity. It's for any finite M, you just get the contribution of the zero modes only.
The first term is just completely cancelled?
The first term completely cancelled, just 1. Both numerator and denominator is lambda squared plus m squared. There are cases when you need to take the mass to infinity to get the topological. You can always work with finite mass, it's just you'll have counter terms, which are, you'll just generate local counter terms. Okay. Mm-hmm.
If you change a bit the Lagrangian so that you don't have this splitting into positive and negative eigenvalues, could you still play some sort of argument by saying that still the operator accumulates at infinity and minus infinity?
I don't think this symmetry is built into the C is some kind of...
No, not that C, the commutation with gamma 3.
Oh. So, again, this description is kind of set in stone at this point. But, for instance, you could consider placing your theory not on an oriented manifold, but on a non-orientable manifold. That's important when you have time reversal symmetry, and you kind of want to probe response to time reversal symmetry. So in that case, the spectrum will not have this form. There will be no lambda minus lambda pairing. So this first term in the product will actually be non-trivial, and that will give you some kind of eta invariant of the 2D Dirac operator. So in this case, this is also in some sense the eta invariant of the 2D Dirac operator, the spectral asymmetry. Just in this particular case, it's saturated just by the zero mode part. Okay. Very good. Okay, so let's come back to the boundary of this continuum theory, right? So remember, we could, for instance, take a profile of the mass with m negative inside our spatial manifold and m positive outside, or we can do this more generally for space-time manifold. And let's see, what do I want to erase? I can actually erase this. Remember, on the boundary, we found a single, on each boundary component, we found a single Majorana mode. Well, what's the action for a single Majorana mode? Well, just this. maybe this is M, and this is the boundary. There's the Majorana sitting here. So what's the partition function of this single Majorana? Well, ddt is an antisymmetric operator, so by the same procedure, this should be the Pfaffen of this ddt operator. But now there is no way to fix the sign of this Pfaffen, right? Because there is no mass term that you can write for the single Majorana, and there is no trick you can play by cancelling out, by kind of fixing the phase by taking the ratio of positive mass to negative mass. So the sign here is ambiguous, and this is a signature of the fact that the single Majorana is anomalous. It cannot exist just in 0 + 1 dimension on its own. But this question of what is the partition function of the bulk plus boundary is completely well defined, and there is the following. The answer is known: bulk plus boundary. You take the absolute value of the Pfaffen of the dd tau living on the boundary, and then you multiply by bulk contribution, and here this is number of zero modes of this Dirac operator that we worked with in the bulk before, but now you need to specify the boundary condition on this Dirac operator, and it turns out to be the right boundary condition here turns out to be so-called non-local APS boundary condition. Ataya Patodi-Zinger. Non-local APS boundary condition. So this is described nicely in a paper by Witten and Yonakura from 2019. So this is an example of kind of anomaly inflow. It's a very, well, it's a bit different from examples we are used to, but indeed it's only the combination of these two terms that makes physical sense, whereas individually they're unphysical. Okay.
So when I take absolute value here, you absorb the phase into the boundary?
That's right. So all the phase is incorporated here. This is just the absolute value. There is actually another issue, which is that if you end up having a Ramon boundary condition on one of these boundaries, right, then the Pfaffen is 0. Okay, so they say, okay, the 0, it doesn't matter what the sign is, but then there are 0 modes living on these boundaries in that case, and if you want to calculate correlation functions, say, of fermion operators on the boundary, you will need to know the orientation on the Grassmann path integral of the 0 modes, and actually the bulk fixes that orientation. So I think that's also discussed in this paper. Yes?
So to connect to Thomas's lecture, so he discussed Maxwell theory, he found an anomaly, and then he provided the anomaly inflow of the 5-dimensional manifold. But for him it was just a convenience. He didn't say that the Maxwell theory by itself is unphysical. So it just represents anomaly, I find the 5-dimensional manifold. Well, here you go further. You say that this single Majorana is unphysical. Why do you say stronger words than Thomas said?
So this is a gravitational anomaly, right? So it's not a symmetry anomaly.
Well, he did not quite explain what he meant.
So here, so for Thomas, the theory itself, Maxwell theory, is perfectly well defined. Then he tries to couple it to a background gauge field for the 2-1 form symmetry, and that once he attempts to do that, the theory is not invariant under gauge transformations of the background fields. So it's only at the step of trying to couple it to the background gauge fields that you run into problem. Here you run into problem kind of at the level of coupling your theory to a metric.
Spin structure.
You can say, well, for fermions, it's always spin structure, right? So it's kind of, I think of gravitational anomaly for fermions. By the way, gravitational anomaly is just placing the theory on some space-time manifold. For fermions, I think of that as including coupling to spin structure. Yeah.
So if you do some diffeomorphism transformations on boundary, it changes the signs of the particular function.
In this case, you're very rigid, right? You just have a circle. The boundary is just a circle, and there is only Neveu-Schwarz or Ramon, so only periodic or anti-periodic boundary conditions. So the usual story of, okay, I have mapping torus, and then I regularize in some way at one end of this mapping torus, and then as I evolve, somehow the sign changes. That story doesn't really apply here, but the anomaly is still there.
Yeah. So the invertible formulatic phase all the invertible formulatic phase can be classified by the mapping torus method?
No.
Just to clarify, for the periodic and periodic boundary conditions, trivial theory has +1 and Kita chain is -1 partition function. But if I look at the form of the partition function, if I just put the sign of absolute value, it doesn't seem to be changing the sign.
So you're looking here on this is on a closed manifold, and this is on an manifold with a boundary. Yeah. Yes.
So is it possible to see from this thing that two of them is not anomalous?
So look here, right? If you tensor 2, just think about closed manifold. You tensor 2 copies of the Kitaev chain, right? The partition function gets squared, so you get just trivial. So that is clear. Yeah. Okay, I think we are running out of time, right? So maybe I'll take.
Would you also emphasize that the gravitational anomaly that you mentioned, the global one?
Yes, it's a global one, and that has to do with the fact that the structure of the stacking group is finite. Right, so
yeah, what about the local?
We'll talk maybe about that next time. But then, in this case, there is no local gravitational anomaly. Okay, let's stop here. Next time we will discuss the fact that this partition function is actually not just a topological invariant, but also a bordism invariant. And we'll pass to general classification of invertible phases using bordism.